that I have to leave 5 minutes to the hour sharp because of some medical reasons unforeseen. So in order to save time, I pre-recorded part of my talk, not very long part, just recalling what was the setting for the last time. And actually the two talks titled Conformal Harmonic Maps of Two Torus to Spheres, but I will end up by constructing such maps. But I will start with describing a new kind of symmetry for very well-known object like ON sigma model. Namely, I will establish connection between Novikov-Veselov hierarchy to show that it is actually a symmetry of the ON sigma model arising naturally in the framework of alternative approach to this kind of equation. So let me briefly recall what was last time. This is the system equation we want to solve. Namely, Qi are solutions to the linear problem subject to the constraint that certain scalar product between Q and Q with itself or bilinear form equals to 1. Here Q and Q, not essentially that this is just a usual scalar product of two vectors. It is just some quadratic form with constant coefficient eta ij, qi, qj. Depending on a signature of this quadratic form, it can be thought as sphere or de Sitter space or anti-de Sitter space. That is not so important. On the level of complex solution, which I will be talking mostly, there is no difference between. So it's in some quadrant. So here U and Q are functions, periodic function on two torus with some fixed complex structure. To avoid some not necessarily technical details, I would like to talk about not just this model, but to begin with its twisted version, which still has important sense in physics. Namely, I will not require that Q be periodic functions. I suppose that they are sections of some line bundle on the torus. So U is a periodic function on the torus, and Q is a section. But in that case, I need two sets of solutions, Qi and Qr sigma, such that they are sections of two dual line bundles, namely their monodromies under the shift in periods of torus are inverse to each other. That's why their scalar product is perfectly well defined as a periodic function. And in particular, the relation between the potential and the solution would be the same if you just put Q. So in this case, so if you express U in Q, that will be a non-linear, highly non-linear equation we want to solve. This is our setting. We want just to solve this equation to begin with. So what is the construction? I was so busy explaining difficulties in Hitchens' approach that I forget to outline what is the main idea. It's very simple, so let me just explain how to construct solutions to this nonlinear system of equation. So we start, the starting point is Novikov-Veselov construction of finite gap or algebraic geometrical potential of this operator. Namely, you start with arbitrary algebraic curve with involution. Sigma is involution. You can think about as permitting two sheets of a factor curve with exactly two fixed points. Then one can define a function, Baker-Hazer function actually, or which is a function of ZZ bar, and the dependence in ZZ bar comes only from its singularity, and as a function of a P, which is a point on the curve. It has standard analytical properties, namely it's meromorphic, its divisor of poles is of degree G, and out in the neighborhood of these marked points, which are the fixed point of involution, it has very simple exponential type singularities. Then, as it was proven by Novikov and Veselov, this psi function for all P solves the differential equation with the potential expressed in terms of prime theta function associated to this curve with involution. The case of 2 points of involution is the only case besides of unramified cover when the prime variety is principally polarized. That's why theta function is well defined. So this is explicit form of the solution. At this moment, I do not discuss periodicity of U. U, for any curve, U is quasi-periodic function of Z and Z bar, because periodicity actually depends on the fact that these two vectors, U capital and U bar capital, are they rational, their coordinates are rational, or there's some multiple are in the lattice or not. Let's look on just on a local solution to this problem without imposing any constraint. Now, suppose that in addition on gamma, there is an even with respect to sigma function with 2m poles, simple poles. You can thought about this function as the preimage of a function on a factor curve where it has m poles. Let's call them pi plus and minus. Then consider the differential psi sigma d omega. I'll explain in a second what this d omega means, times E. This is a meromorphic differential, on gamma. Why it's meromorphic? Because we assume that the local coordinates k that enters in the exponential singularity is odd with respect to involution. That's why psi and psi sigma, this is the product of 2 psi on 2 sheets of the cover, exponential singularity cancel each other. The condition on the divisor that it is canonical class plus p plus and p minus means that poles of psi and psi sigma are canceled by proper choice of meromorphic differential d omega having simple poles at points p plus and p minus. So what is left? This is meromorphic differential. Sum of its residues, let's call it d omega tilde, residues d omega tilde is zeros over all residues. Where are residues of this function? The residues are at P plus and P minus, where we have simple poles for d omega tilde. So the sum of these residues is the difference, because the residues of d omega are of opposite sign. The difference of evaluation of this function at these 2 points, and that equals to the sum of residues. And where are the remaining residues? Only where are poles of E. So we're getting that this is sum of Ri psi evaluated bar at P I plus times psi evaluated of Z bar P I minus. So we have the quadratic relation where Ri are just residues of a constant, so they're constant of d omega. They do not depend on z bar. So we get the solution. Evaluation of this function, Baker-Heisel function, at certain points, and the opposite, exactly after dividing by e some constant, satisfies the constraint. And by definition, they are solutions to the linear equation. This is the solution. Very simple argument using only residue theory. And it is much easier in this approach to put additional constraint on solutions, because, as I said last time, condition that the corresponding harmonic map is conformal requires a certain scalar product of QZ, UZ bar, QZ, QZ, or sigma to be equal to 0, so-called Virasoro constraint. Again, in geometric terms, it's very simple to satisfy. Is equivalent to the condition that this differential of this function is 0 at points P plus, P minus. Again, it's hard to satisfy. It's not clear how to do it in original approach, but in these geometric terms, it's pretty obvious. For example, you can take a cover of hyperelliptic curve branched at 2 Weierstrass points of a hyperelliptic curve, and you are done. You have conformal harmonic map. Again, I'm putting at this moment aside periodicity constraints that are hard to satisfy. They are hard to satisfy in both approaches. But let's look again on this system as just some nonlinear system of equations, local, without boundary condition. We'll come to that later. Any questions? There are basically equation. Y, E. You see, the construction is it's around for quite a few number of years. I used it about 25 years ago. And there was no clue to understand, is it all solutions? What is it a tiny portion of solutions? So why E? The idea works, it gives solutions. No clue why the existence of a function, meromorphic function, is additional structure for a spectral curve of Schrödinger operator. So the answer actually was obtained in our previous work with Nikita. We proved, sorry. So this is, and Nekrasov. We proved actually that if gamma is of finite genus, so if we are dealing with algebraic integral potential, finite genus, and is irreducible, then the existence of E is not only sufficient, is sufficient that I'll just prove it, sufficient and necessary. So this construction gives all solutions to the equation in the case of finite genus algebraic potential, finite genus spectral curves. The proof is far from obvious. It is used some analogs with the Seiberg-Witten theory, and I'm not going to present it today. If there would be question, I'll be happy to describe, but let's leave it as it is. Because the other question remains, is it necessary for gamma, which is a spectral curve, to be a finite genus? Okay. Of course, that is only, and that I'm going to outline the proof. That proof requires some periodicity condition and ellipticity of the problem we are considering. So, and for that, I want, again, start a little bit aside. Namely, what is the first advantage of having Lax representation for equation of some nonlinear equations of motions? Lax representation leads to family of commuting flows on the space of solution. So from Lax representation, you have integrals of motion. Usually you use them as Hamiltonians. They produce commuting flows, Hamiltonian vector fields, space of solutions. In this approach I'm describing, again, there is no, at first glance, even traces of these symmetries. Just solve the given equation. What are the symmetries that preserve this system? So the obvious candidate for this symmetry would be the symmetry conjectural answer the symmetry of Schrödinger operator, of operator dd bar. I'll use H for further use of this operator. And that symmetry are called Novikov-Veselov hierarchy. I'll describe it in a minute. Unfortunately, our original idea that it would be very easy to show that this symmetry, the symmetries of this equation preserve the quadratic relation, turned out to be highly non-trivial. I have to confess, we spent about 3 months trying directly to prove it. It can be checked by hand for first 2 floors that they indeed preserve this quadratic relation. Then Nikita even wrote a small program to check for 3 more. There are some remarkable consolation. At the end, they do preserve. And there was no clue how to prove it in general. So what I'm going to state is, again, it's very simple, but it's like a solution of a problem and some Olympiad. It's 5 lines, but to find this fine line, it's very hard. So what is the Novikov-Veselov hierarchy? Novikov-Veselov hierarchy. It is defined on a space of pseudo-differential operators, LD, sum of VI, ZZ bar, D minus I runs from 1 to infinity, is pseudo-differential operator in DZ with coefficients that are functions of Z and Z bar, and they're subject to the constraint such that L commutator with H equals some pseudo-differential operator in D and differential operator in Z bar H, or it's 0 modular principal ideal generated by H. So it's not like usually in the Lux theory, then the commutator equals 0. No, it is not. It is not only modular some ideal left ideal generated by H. So why that has sense? Because if you have a differential operator in D bar and D, I'm just marking as a Newton polygon powers of non-zero coefficient. So you have pseudo-differential operator in D bar and pseudo-differential operator in D. And in this ring, in factoring, any differential operator containing positive power of D bar is divisible by H, because H has the first power in D bar. So you can divide. And so this ring is isomorphic essentially to the pseudo-differential operators in DZ only. You can just write the current system of equations, very simple one, that defines evolution of V in Z bar. So for example, V1Z bar equals UZ, V2Z bar equals some function known explicit polynomial in U and V1, differential polynomial, V2Z bar. So you see, on each step, you solve the freedom in defining V is an initial condition. So you may think about this phase space as a space with coordinate, this is original function u in zz bar, and functions vi of z0, like initial condition. So it's almost the same as pseudo-differential operators in KP theory, but now you have non-trivial dependence on z bar. So having this space, the evolutions, commuting family of evolution is defined very simple. So more or less identically to what we have in KP theory. So derivatives with respect of nth time of the floor, of nth floor, is defined as commutator of L to the power 2n plus 1, strictly positive d plus, strictly positive part of d. So you have set the differential operator, you take all coefficient with positive powers of dz, and that is the definition of plus with L. This is the equation that describes evolution of your pseudo-differential operator L, and evolution of U is defined by the equation dn equals the residue of this L to the power 2n plus 1 as pseudo-differential operator. So the coefficient of this operator in front of d minus 1. Some work is needed to show that these flow commute and preserve our space. That is indeed the symmetries. It's a little bit more involved, the proof, than in the usual KP theory, but not significantly harder. Okay, so what is neat? So this is the symmetry that preserves spectral curve of the Schrödinger operator by its definition. In order to show that this is the symmetry of ON model, in order to show that that it is a symmetry.
Igor, quick question. The ON, the N in the ON, where does it enter in this setting? Is that
ON is dimension of this vector Q.
right? But in this in this hierarchy we're discussing, where
No,
is that?
there is no traces. It's absolutely, it is defined as a symmetry of the equation, linear equation. We want to show that it is in fact a symmetry, namely, if in addition this equation d minus u has a family of solutions, namely there must be solutions to evaluation of our function at certain points. If q at certain moment equals to 1, we need to prove that this symmetry and how this symmetry acts on q dn q is L 2n plus 1 plus q. This is the evolution of q.
Oh, it's just scalar? It's got like a scalar thing?
Yes,
L
it acts as a scalar on each coordinate.
Okay.
Because you see, these q are evaluation of some scalar function. It's very so we define such a symmetry in such a way, and we want to show that this symmetry preserves the quadratic relation.
Okay.
So That is equivalent to the fact that if you apply this, okay, let me just write ln for brevity, q, that would be 0. ln is by definition this differential operator. So there is explicit definition of ln, there are q's, and you need to prove this identity, because it means that the derivative along this flow of q with q is 0, so the relation, quadratic relation, is satisfied. Again, and that's why it's so hard to prove, because it seems that these two things are absolutely unrelated. If you if you don't use algebraic integrability. No, this is, again, how one may try to prove. What we need to show, we need to show that the sum omega I di q is 0. Omega i's are coefficients, sum of di omega I runs from 1 to n plus 1. Again, it's very easy to write the recurrent system of equations on these moments. Oh, let me just show. Let you know, Ti would be the scalar product of Ti q. You take the derivative in bar, use that each q is a solution to this linear equation, you get Ti would be scalar product of di minus 1 uq u minus di q d bar q, and then just integrating bar parts. I don't want to continue this equality. What you will get a system of equation d bar ti expressing fi through t's with j less than I minus 1. So just, and this, so you can recurrently compute all these moments. And this system looks very similar to the system that defines the coefficients. So originally we thought, okay, there are two recurrent relations. We'll immediately get that these two vectors are orthogonal. And again, you can just put in Mathematica and immediately compute as many flows as you wish, with no clue why all terms at the end cancel each other. So I'm afraid I have no way. I can prove it in 5 minutes, but probably let's postpone it if there would be time. So again, the proof is the Novikov-Veselov hierarchy preserves a quadratic relation. So what's the basic corollary of this? The basic corollary of this is that LQ satisfies the equation d bar because it's a symmetry. We can take the derivative of linearize our system on the background of some solution. And we see that this ln q, again, this is a vector, q is a vector, ln is scalar differential operator applied to each coordinate, and it satisfies the equation d bar of ln q u minus d bar q d l n q minus dq bar ln q equals 0. This is just linearized equation, our equation on the background of known solution. So ln q solves the elliptic equation on the torus. The kernel of such linear operator must
Apply maximum principle.
okay. The kernel is finite dimensional. So out of infinite symmetries, because n runs from 1 to infinity, there is only a finite number of laws in the linear independent. Then that implies that the genus of the curve finite, and we are done. So the scheme I explained at the beginning gives all solution to periodic to the periodic ON model, or describes all harmonic maps of two torus to the sphere under the assumption, and that I said, if this curve is, the spectral curve is irreducible, because only in the irreducible case, the proof we found with Nikita works. There is one particular case. It's even stronger than the condition of the conformal harmonic map. Conformal harmonic maps, conformal.
Igor, I apologize. The picture when you talked about the curve, the picture you drew was reducible, but then you really meant irreducible, right?
No,
it
is irreducible. The curve is irreducible. I try to draw the picture as two-sheeted cover.
I see. Okay.
With 2 points, 2 branch points. Yeah. No, the curve is irreducible.
But you're saying that there's obvious case where you just have two components which the involution permute, and they say this is something else. You're not talking about that case.
I will talk about this because this case is the case when all these moments, which I said DIQ, they are identically 0. Conformal maps are conformal maps are those for which T4 equals 0. The fourth moment is 0. This is something, I don't know what is the proper name for it, holomorphic, because it is actually the case for instanton solutions of instanton maps of two torus to S2. And that corresponds to the case when the corresponding curve is reducible. Again, a toy example of situation with reducible curves is, remember I described the simple basic curve d bar minus a constant minus u naught equals 0, which can be easily solved. A corresponding spectral curve was defined by the equation P1 square minus P2 square equals u naught, something like that. It's irreducible curve. The only special case when u is equal to 0 So if u is not 0, the solutions would be, of this equation would be u equals ekz plus 1 u naught over k z bar. This is the solution to this equation when u naught is equal to 0. If u naught is 0, there are simply two branches. On one, e psi would be just ekz. On the other, psi would be ekz bar.
Mhm.
This is, so u0 is the example of reducible spectral curve. I will not present today, I simply have no time to explain that if you consider now your curve, spectral curve reducible with 2n plus 1 points of intersection and two marked points we talked about are on separate, on irreducible components. This is p plus and p minus. You can generalize, further generalize Novikov-Veselov construction. And again, you get the solution to our problem. There is no function u in E in this case, just from analytic properties of corresponding Baker-Heisler function, which can be thought as a section of some sheaf. Now it's a sheaf on this singular curve. You will get the solution to the problem in question.
Mhm.
I just want to explain one important point. Namely, it turns out that for those solutions, the periodicity constraint I was talking all the time, you can write them, you cannot solve them. They become solvable explicitly. So all these maps are explicit. This is the first time when they are obtained. Let me just explain why. So when you have irreducible curve, spectral curve with 2 points, what are conditions that are needed to be satisfied in order to get periodic solutions? You have two differentials, dp, having simple pole at, not simple, pole of order 2 with no residues at these 2 points. So dp1 is dk, k, dz over z, dk. I prefer write k as z inverse. It's inverse to a local coordinate. At one point near p plus, dp1 is differential having exactly the same type of singularity at the point p minus. And dp2, this dpi are logarithmic derivative d of log Bloch multipliers. And as a result, and the local singularity at these points are of this type, dp2 equals tau bar dk. And the periodicity requirement that you need from this definition, this differential has to be pi. All periods should be in integer modulo 2 pi. No. 1 over 2 pi I. They have to be integers. And condition that certain periods are integers, just again, unsolvable. What's the difference? Now we have this condition for two differentials on each component. And on each component, each of differential dp1 and dp2 has just one pole of second order. Consider their difference, dp1 tau minus dp2. It is holomorphic differential because when you take this linear combination, the poles cancel each other, holomorphic. And that means that periods of this differential omega are in the lattice. And that means that this curve is a cover of an elliptic curve. Immediately you need a little bit more work to show that this curve is not just a cover of an elliptic curve. The irreducible component is the spectral curve of elliptic Calogero-Moser system. And you are done because this family of curves is explicit. It's written by algebraic equations. So splitting 2 points actually allows you effectively solve the periodicity constraints that are transcendental in general. What is remaining and very challenging question? You see, again, in all literature on these periodic sigma models, the question about always about periodicity constraints are considered as transcendental. It's not exactly true. If you know at least one solution, so the tangent space to the corresponding modular of curves is algebraic. It is described by some subbundle of a Hodge bundle. So if you know at least one point, you can explicitly construct integrating along the tangent line all the other curves. The question is how to construct explicitly at least one example for any n. As I said, in his approach, Hitchin succeeded to construct them only in genus 1, 2, and 3. That's all. Here we have example of a spectral curves for any n, for any genus. This genus corresponds to the number of particles in the Calogero-Moser system. Unfortunately, the variation, so the intriguing question is, when the curve is irreducible, there is a presence of some function E. You come to reducible case, it disappears. So the question, how to write the perturbation of this reducible curve to make it irreducible? Where these poles of this function E goes? Do they go simply to some rational components between these irreducible components? So probably it's not like just the intersection of two components. Probably in between, there are some CP1s included. So it's very interesting to understand how degeneration of irreducible curve goes, because if you solve this problem, then you can just pretend that you can solve in general periodicity constraint. You have a starting point, this is singular curve, you perturb, you are done. That is the problem we're looking right now. Okay, I have to stop, unfortunately. Any question? I have 2 minutes to answer if there are any questions.
Questions? Let's have, if we don't have questions, let's have 2 minutes of applause for Igor for giving this presentation through all the difficulties that he had to overcome. So thank you so much.
Okay. Thank you.
Yeah. All right. So next week it's Edward Frankel, which will be on the whatever on the schedule soon. So I apologize for, and so that will, and I'll see everybody. I'll see everybody then. Until next week. That's all for today.